Good afternoon, everybody. Ruben Miranda from Duff and Phelps. Got a brief spectrum update. I know I'm keeping you guys from lunch, so we will definitely break at the scheduled time of 12:30, so this will be a relatively quick one. Incidentally, I did not get the memo about needing to wear the outfit, so apparently some of us know how to dress ourselves. Jim. We've had some key takeaways. This is my third installment of presenting on spectrum for the wireless side. And what we've typically seen is that the spectrum valuation, the costs that have been incurred in the auction have really been maximized on coverage. So the better it can propagate, the more it's been valued. And so you can see that relationship there. Low band was definitely considered more premium to the mid and the high band. And that was until around 2014. And then when I did a follow-up back in 2018 on the more recent auctions that had taken place, what we had seen was that some of the, after you do these massive regression analyses of the different types of auctions, there's definitely lots of considerations to be made. What sort of income ranges are being offered in the areas that they're auctioning the service. Along with the median age, because that matters too, whether or not the spectrum is paired or non-paired, and then also the density as well. That's a consideration. But we were noticing as of, for those two different auctions, kind of before 14 and after 14, the type, whether it was low band or whether it was mid/high band, there was a coefficient swing of about $1 more in pop megahertz. What does that mean? Well, that meant that the carriers were valuing the mid and the high band stuff, all things equal, about $1 more per pop megahertz. And so clearly there was something going on there. And then we identified that there was possibilities of they were valuing the mid-band just because it was a bolt-on to your existing service, to your existing coverage service. In other words, you're providing capacity value on top of that coverage value. So, we kind of left it at that, saying, well, let's take a look at the millimeter wave auctions and take a look and see if we could get an answer from that. And our early results were pretty mixed. I mean, we'd seen that by and large the ultra high, the millimeter wave spectrums, and you have to applaud the FCC for just ramming this through. I mean, they had 3 different auctions taking place in 2019 alone, so they are trying to get this out as quick as possible. They had the auction 101, the auction 102, and auction 103 I think is still going on, or it may have just wrapped up. But that's a lot of different megahertz that they're auctioning out there. And on the whole, it's coming in right around like a penny per pop megahertz. But I think there's a lot more going on there than just looking at the megahertz pop story. And to do that, I want to walk through some examples of just how the spectrum works and how exactly they're going to get millimeter wave to deliver those promises of gigabit speeds. I presented a version of this presentation with the IAAO conference in Florida. And I think it's a useful primer just to help you understand how millimeter wave works and how much better it's supposed to deliver 5G. I always like this graphic just because it describes an information superhighway. I think describing spectrum as a highway can be very useful because it's a very good analogy. Here's the picture that I have set up, and if you describe the highway as the frequency block, let's say for any given block, if you're in 700 to 710 megahertz, that block, that's 10 megahertz. That would be the lanes of the road. So you have 10 megahertz wide channel to get through. So you have a 10-lane highway. And this example kind of shows it. So you got 5 going one way and 5 going the other. And then you got all the cars and the trucks on the road, which are just the data bits. It's the stuff going from one side to the other over the frequency. And so to illustrate the analogy, we then say, okay, so how do we get more cars and trucks moving through this pipe, through this highway? And there's 2 ways that you could do it. Well, the one is, you just have them go faster. Instead of going 65 miles an hour, have them, raise the speed limit to 80. The other one is you could just add more lanes. So you just, bolt on some more lanes like we love to do in Houston. and those are really generally the two ways. Now, of course, there's more technological things going on there, but I think this is it's more of a simplification than anything else to describe how you're going to get, more of that data, more of the speeds that people are wanting. That solution, number one, to make the bits go faster. You could also think of the analogy being, well, the cars and trucks, they have a hypothetical speed limit in their current form, and that is, where the rubber meets the road. Only so much speed that you can do. We're not in the Hyperloop just yet, so we don't have that frictionless capability. There's always going to be the drag and just the physical means that limit us from going 200 miles an hour in the cars. And so radio transmitters and those headset modems, they also have kind of that similar bottleneck. The technical term is the Shannon limit, and that's a very difficult number to improve. I mean, once you get to a certain point, once you improve the generational technology, if you go from 4G to 5G, yes, you have that improvement. But within, once you have that framework, it's definitely hard to get it to move any further. You could also think of this as spectral efficiency. This would be described as a megabits per second per megahertz, or in the analogy, you would be thinking of it as miles per hour per lane. So you have one lane, and then just how fast a car can go inside of that one lane. And like I said, it's really hard to increase that number just without a huge effort from the 3GPP. The other solution that kind of described earlier was to add more lanes. Currently the average auction license bandwidth since prior to the millimeter wave auctions has been about 10 to 20 megahertz. And so the frequencies that they're talking about is massive, that they need to be able to deliver for 5G service. They're talking about much bigger frequencies. Instead of 10 to 20 megahertz, they're talking about 100 to 200. Now, just instantly like that, you can think of it as a 10x increase in speed. So you have 10 times more channel space, 10 times more speed. Well, the only place that you have that currently in the United States is in the ultra-high millimeter wave spectrums. Craig Moffett, I think, said it best, that they were set for those insanely wide blocks of spectrum for 5G, and you can't find that anywhere else, those insanely wide blocks, except in the 5G, except in the stratospheric high frequencies. So you have this large opportunity there to deliver service, and compared to what you had available for 4G, they're just talking about making more highway lanes. That's it. And then the special case for 5G is that it's introducing, because of the technologies that they've implemented, it's had this byproduct of increasing spectral efficiency, but depending on the frequency that you're at. I have this graph here on the left. This is all from the CTIA, which describes the generational improvements in spectral efficiency being bits per second per hertz. You go from 3G, which is 2.6, to 4G, which was 15. I mean, that's a pretty good bump, 2.6 to 15. But then when you're talking about 5G, you're really only talking about a 100% increase, which a relatively disappointing metric. But consider that we were just talking about it. It's very hard to increase that limit. So this is the magic where 5G does better. 5G does better in the higher bands, and that you have now this capability. Well, if you're deploying 5G on low band, you're not going to see very much improvement, only 20% over LTE service. But if you're in the mid band, you start to see an improvement up to 50% faster, and you can only see where that's going. So as you go further up the spectrum, you're going to get an increase in the spectral efficiency. And I have this example to show, well, on the next slide. But when you're running better on higher frequencies, you consider, per megahertz channel, the 800 megahertz, the one that goes furthest. If you go to 5G, you're only going to get about a 20% bump. If you're going in the mid band and the high bands, you're looking at a 50% bump. But in that 30 to 300 gigahertz, which is generally considered millimeter wave, you're looking at a 100% improvement at least. Here's the example that I have. If you're on low or mid and you have a channel width, the average channel width being 10 megahertz, if you have a spectral efficiency of 15, which we saw on the previous slide, and you allocate some of that frequency for download and also overhead, then you're looking at a LTE speed, an average LTE speed of about 56 megabits per second. Now, when you improve that, if you go to the spectral efficiency improvements that 5G offers, at low band, you're talking about a 20% bump. Mid and high, you're talking about a 50% bump. Then you can see the improvements. On low band, you go from 56 to 67 megabits per second. On low and high, you'd go from 56.3 to around 85. But then look at millimeter wave. So if you're talking about 43 gigahertz speed, they're talking about implementing a 100 megahertz channel, which, again, a huge pathway. So you're already going to get a 10x improvement in speed. Now, when you compare that to the spectral efficiency that we showed in that example being over 100% higher, then you're doubling the spectral efficiency, and then you're adding 10 times more channel. That's how you get to gigabit speeds. I mean, that's the strategy right now in the United States, is you want to deliver that, then you're going to have to do it on millimeter wave, and you're going to have to do it with very high channels. So yeah, I mean, you talk about 4G, the existing bands, you're probably getting 56. You're talking about 5G on millimeter wave getting you those gigabit speeds. And that's a 10x increase in the channel size, but it's a 19x increase in speed. That's kind of the promise that 5G is offering. The layer cake analogy, I think, is a really good one. T-Mobile had this presented last year, where they talk about the low band nationwide, really focusing on the coverage, and then the ultra high being the dense urban millimeter wave, and that's going to be the capacity. And that missing middle right there, that mid band, is really going to be where the future of 5G is going to be. You don't have the capabilities currently of the millimeter wave speeds there, but you also have better coverage than millimeter wave here. So it's, you're kind of trying to find a happy middle. And currently, mid-band, and we should mention this too, I think there are some, conventions about what mid-band means. For this purpose, then we're really talking about anything below, 5 or 6 gigahertz. And so some might call that high band, some might call that, mid-band. I tend to just lump it all together. There is definitely a differentiation in how you describe those. I would probably refer to this dense urban millimeter wave as ultra high. But it really depends on how you're defining it. That being the key, I mean, the millimeter wave is not going to be a coverage frequency. It's going to be absolutely going to be capacity. I got some quotes from some of the carriers that talk about that they're never really going to materially scale. You're talking about dense urban pockets that are going to get that. Even the CEO of Verizon says it's not going to be a coverage spectrum. Millimeter wave is just going to be isolated. And really telling here, the CEO of the Verizon Consumer Group says that, you can deploy the 5G offering, but the lower the spectrum tiers you go, the lower you get to that low band, the more that's going to approximate to a good 4G service. And I don't think a lot of people are going to be very happy when they turn on their 5G phones and they realize they're only getting 20% improvement. I think there's going to be a lot of disappointed people. So to summarize, we're talking about the historic drivers being propagation. Further out you go, the more valuable it is. I think you're seeing a real shift in where those drivers of price are coming in. Not only are you seeing where the spectral efficiency is better for 5G, so the higher bands are now more valuable just by that very nature, but then you also have availability. I think Chuck Noll once said that the best ability for his football players was availability. And so that's the value, is having that spectrum freed up to be able to use. And that's becoming a highly desirable area where you can carve out 100 megahertz channels to serve customers and maximize those speeds. So low band is going to maintain some value, but we're talking more about coverage value, not really capacity value. And so I think there's going to be a lot of confusion, even now and going forward, about what is the right way to value it. Is it going to be a coverage value? Is it going to be a capacity value? I think they need a whole new metric to talk about tracking what spectrum values are. I don't think what we're seeing is going to make much sense going forward. But again, I mean, this is really a story about the disappointment that people are going to see for those low band deployments. Limited channels, low improvements in spectral efficiency. You know, the carriers that have been rolling it out have been promising more to come. And the reason is because they're trying to get that mid-band freed up. You know, once they get that mid-band freed up, then they'll be able to provide the improved speeds. But for now, you know, there's going to be a lot of fish shaking at these carriers because a lot of what's been promising is not going to come to fruition for, you know, many more years to come. Okay. Any questions? Bill?
What's the interplay between all of that data going down through TCP/IP links and therefore more people within? Yeah. How much of that does the impact of using, well, basically, I'll be techie for a minute, RAN, okay, software-defined networks and RAN, tied into RAN. How easy can it be managed? How many real-time conversations can I have? That kind of fast response to an IoT going up to the hurricane headquarters.
Well, I think if you're asking about the edge and whether or not the software-defined networks, I think it's all part of the 5G implementations that we're talking about. I mean, this is really a simplification to describe, you know, how we can equate the availability of spectrum and the propagation characteristics of the spectrum. I don't know, because of the time window we have, we don't have really a chance to focus in on where those, you know, where the edge impacts this.
Also factors in the cost in there.
Yeah, I mean, that's a good point. You know, the fact that they're bidding and getting spectrum for $1, you know, on the older, larger, low-band deployments for the Auction 97, and then you're talking about 1 penny per pop megahertz for the ultra-high frequency. Well, there's a reason for that, too. It's because, you know, that propagation for that ultra-high isn't going to go very far. So you need to put in a lot more of those supporting equipment. You know, a lot more antennas in place, a lot more utility poles have to be, you know, in the area for you to install and get attachments for. But, you know, the investment equation becomes a little bit more murky when you're talking about 4G versus 5G.
I have a quick question. We haven't talked a whole lot about fixed wireless. Does that work into all this? And there's the range for the high frequency spectrum better for a fixed wireless approach?
You know, I don't know about the use case yet of fixed wireless using millimeter wave. I think by and large they're focusing more along the dense urban environments and not so much on you know, building it out for you know, say apartment blocks. I mean, you can imagine, you know, if you've got a suburban environment, you know, and then you have an apartment complex. Well, suddenly you've gone from a not very dense network to, you know, to a very dense populated network. I mean, those millimeter wave networks, you know, will take time to develop. And if you're talking about just going use case by use case, that's going to be a long process.
Do we have any other questions before we break for lunch for Ruben? All right, well, we're right on time. Good job.